Hi, Sunil.
Hi, Gautam. How are you? Good
Good.
morning. How are things?
Good.
How are Oppo, Srishti?
They are all fine.
Fine.
She is here, so that's a great thing. We had her for so many months now.
Yeah.
Hmm.
Where is she? Where has she been all this time? I'm lost.
She is doing BTech in VIT
Oh, VIT. Okay.
in biotechnology.
I see.
So she is finishing this year.
And it's all online since last few months?
Yeah. So her college closed down by March, in fact, middle of March. So it was already getting very difficult to find tickets for her. So just about in the last few tickets she could come.
I see.
Yeah. And the last semester is a research semester. So that is also going to be outside. So that's
I see.
right.
Okay.
Hi, Vedang.
Hi, Gautam. Thanks for giving this talk.
You're most welcome. Are you in your office?
Yes.
So am I.
Sunil, you are also in your office, is it? No.
Yeah, I am.
Yeah.
I come every day. By some strange luck or choice, I don't know. My office actually isn't next to any other office. It's in a corridor with AC, some electrical unit on one side and some other thing on the other side. So
Oh, wow.
blissfully isolated, and I have a window. So everything I could want.
Oh, you have a window. I see. So you don't have centralized
No,
this
have.
thing. No.
Oh, you haven't been here, or you have probably been here only for a conference, not to the main building.
Yeah. I have been there for a conference. Yeah, but by the time the new yeah, I was.
Yeah, Sunil, maybe you should take this opportunity to remind Gautam how good the weather and in general the air conditioning is here in Pune compared to TIFR.
Yeah. Pune is naturally air conditioned. So we have absolutely, most of the year we need nothing, neither fan nor AC nor nothing, nor heating either. Like just now I'm just sitting with window open 1 inch and that's that. And Diptima is even wearing a sweatshirt.
Yeah.
That's because he's Bengali. So below some threshold they start wearing, or you're not wearing muffler and all that.
And no. It's just because I took my motorbike to come.
No, he is not a real Bengali, because then he would have put on the monkey cap.
Monkey cap, yes.
No, I'm not a real Bengali for many other reasons. I'm a vegetarian. So according to all Bengalis, I am a Bengali anomaly.
No, you are immediately written off.
Yeah.
No Bengali worth the name can be a vegetarian.
In fact, one of my Bengali friends once make this strong comment that no self-respected Bengali will not eat fish.
Yeah. So I was with that.
Yeah, fish is in fact part of vegetarian diet.
This whole conversation is happening in front of 30 participants who I hope no one is getting offended, but I assume not.
So Diptimai, how are you?
Yeah, good. I have very nice colleagues. One of them you see in front of you, so I'm very happy.
That's another thing. My office is on the way to the bathroom, so people stop by. And they can see through the window if my light is on. So.
But you see, in spite of the fact that Sunil's office is slightly isolated because of some not so nice colleagues, he can't be so isolated from everybody else.
No, I chose this office. No, not so nice colleagues. In fact, this office is absolutely ideal for me. I can even see the sky from here. Very nice.
He has colleagues who drop in for all kind of reasons in his office.
No, stop chatting now. There's a symposium to start.
Yeah.
Vedant, are we starting now or are we waiting? Or whoever is the host?
Yes. So you are the chair, so please start.
Yeah, should I start now?
Yeah.
Okay, so I welcome all the participants to this day of 18th December and this session, which is called Formal Theory. There are 3 talks. Each talk is of 40 minutes. So the talks should be 35 minutes and leaving 5 for questions. And so I'll maybe warn the speakers at 30 minutes that they have 5 minutes left. And before we start, I've been asked to say a few things. So microphones are to be strictly muted. It's a very common problem that people forget to do that. Except, by the way, the speaker, they have to be strictly unmuted. And that's also a common problem. Then asking questions during the talk is discouraged unless it's a very short and basic intervention, like if there's some typo or something important. Questions can be asked after the talk using raise hand or chat window. So I'll try to monitor the chat window. And for post-talk discussion, there is a Slack workspace which people may join. So now I'd like to invite Professor Gautam Mandal to give the first talk. This is an extraordinary pleasure for me, as he has been a colleague for most of my academic life, and he's presently the chair of the Department of Theoretical Physics at TIFR. And he will talk today. Now something has happened to my window. Oh, if you full screened. Sorry, give me a second. Yeah. And so he will, really sorry. There's so many mails that I end up losing them. Good. He will talk about bulk entanglement entropy and quantum quenches. So Gautam, please start.
Thank you, Sunil, and thank you to all the organizers of this conference for inviting me here. So my talk title looked a little weird with A/B, but which meant that it's either A or B, and I'll choose. I had actually chosen, but it's not been updated. So I have chosen to talk about B, which is quantum quench. So the story that I'm going to say briefly is a story of quantum quench, and basically long time behavior of dynamical systems post quench, and I'll explain what these things mean in mostly low dimensions, 1 and 2 dimensions, where there are lots of experimental systems as well as powerful theoretical techniques available, but I will also briefly mention about higher dimensions. Okay, so let's see. These are my collaborators. This project has been going on from 2013, and based on, and today's talk will take a lot from earlier works by me and others on C=1 models. So, but I'll tell you the general background as well. Okay, so the long-time dynamics of non-equilibrium states, that's what we will be interested in. So this, of course, is a question of great interest, both from the point of view of experimental and theoretical point of view, and as well as, in fact, practical point of view in several cases, like friction, the time scale of relaxation, and so on. And also, of course, about the qualitative statement about whether the system equilibrates, which is some statement which has been investigated for long times, from even before the times of Poincaré, who introduced topological methods to see whether like the solar system retains its periodic motion, or it goes into equilibrium. So there are some instances in which we don't want equilibration, and in some other systems, of course, we do want equilibration. So does the system equilibrate in terms of what variables, which states, and what systems equilibrate? So that's one broad question. I mean, just looking at the Hamiltonian of the system, you may not be able to immediately realize or whether the system equilibrates, because it may also depend on what kind of observables and what kind of initial states are being used, and so on. So this is a long story, and this is a very widely studied area. Okay, and the nature of the equilibrium. So even if it equilibrates, whether the equilibrium is given by thermal ensemble, or in a way, as we will see, that even integrable models can have equilibration, in the sense that it's some kind of the equilibrates to some kind of super grand canonical ensemble, which is called the generalized Gibbs ensemble, GGE, and the generalized Gibbs ensemble. Just give me 1 sec. I need my pen. Just give me 1 sec. Sorry. Okay. Yeah. So here, so I was talking about this stuff, GGE, or there are systems which are called systems with many body localization. So they retain their memory. So although the system arrives at a steady state asymptotically, but it remembers what the initial states are. So there are various types of nature of equilibration. And there's also the Kibble-Zurich phenomenon, in which you start with some so you have some transition across dynamical transition across a phase transition point, and it retains the some memory of if you go from ordered to disordered, etc. So there is a very broad area. So there are quantitative questions one can ask. So rate of approach to equilibrium, whether in particular whether it goes to equilibrium through an exponential, something like e to the power minus gamma t, or power law, and in which case what are the exponents. And the idea, of course, in this, since these are very general broad questions, the idea is to look for universality classes of equilibrium states of and of also relaxation rates, in particular in those situations involving quantum quench, as we'll come to. Okay, so quantum quench is a very popular method of creating non-equilibrium states, both theoretically as well as experimentally. So there are two examples here in which this is an Ising chain with a transverse magnetic field, this HFT. So without the time dependence, this is a normal Ising model with a transverse magnetic field. And a quantum quench involves in giving a time dependence to this parameter, and you can basically you can go from some initial value to a final value. And one interesting set of questions arises when the initial value is the final value is such that the system is critical. Okay, and is described by a conformal field theory. And here's another system which is more familiar to the audience today. I believe that this is like a scalar field theory, free field theory. Free field theory is a particularly simple example in which shows a lot of this also shows a very rich phenomenology, surprisingly, that the mass of the scalar field is given a time dependence, and one particularly interesting class of quenches is something in which the mass goes to 0 at the end of the time variation. And typically, you do the time variation in a very fast manner. So it's called a sudden quench. And so if you start with the ground state of this system and change the mass to 0, then you can ask what is the state that is created, and how in terms of the new variables, and how does it equilibrate. Okay. So that's the class of questions called quantum quench. So the methods of solving the post-quench dynamics. So primarily these are numerical methods, because given an arbitrary system, you may not have analytic methods available. But in the last decade or so, there are lots of very interesting works in this area, pioneered by Calabrese and Cardi and Rigol and Srednicki and so on. It's more than a decade now. It's 15 years or so. So what are the systems that have been basically looked at? So 1 plus 1 dimensional theories, in particular conformal field theory, that is to say when the post-quench system is given by a conformal field theory, and free field theories. So these are the systems which we will briefly mention. So 1 plus 1 dimensional conformal field theory, free or large n when field theories in arbitrary dimensions, and the thermal or GG state. So we will investigate the final equilibrium state and show that they actually correspond to thermal states or the GG state in case of integrable models, as well as we will find a relaxation rate dictated by universal CFT properties. So we will we will not, so these are the things that we have found in these papers, and this is not, we are not going to go into the details of these things. So one interesting result that we found very recently, last year, is that if the number of spatial dimensions is odd, then the equilibration is to the, so this is in the case of free field theories or ON field theories, that it equilibrates by an exponential relaxation, and if the number of spatial dimensions is even, then it equilibrates by a power law relaxation. Okay, and the particular exponents gamma and p, they are related to universal properties of the field theory that is under question. Okay, the other method is holography, and in which case, for example, the relaxation rate is the equilibrium state is sort of related to a black hole state, or in case of integrable models, it is related to higher spin black holes. So there are such objects in 3 dimensions, and the decay of a scalar perturbation back to 0 in the background of such black holes is called quasi-normal decay, and the relaxation rates in the boundary field theory are related to quasi-normal decay. They're the same as a quasi-normal decay. So that's another method in which you can find the relaxation rates, is by computing quasi-normal decay rates. And the other method, which again allows you to do, in an ADS CFT context, it allows you to do the boundary field theory calculations as well as the bulk calculations, is the SOIK model. And you can make a lot of interesting statements about thermalization and black hole formation and so on. Okay. But these are not the things that I will sort of go into detail in this talk. So, so in this talk, I'm going to talk about a new method in which we tackle these thermalization properties, Surprisingly, this is the classical method, and allows you to talk about thermalization because there's a large number of particles. So in this talk, we'll discuss the application of phase space hydrodynamics. This is essentially classical, and I'll tell you how we can tackle thermalization in this in a classical way. So what are the systems? The systems are the large number of fermions. Mostly our discussion will be 1 + 1, and in a limited way in 2 + 1 dimensions. So so these are some. So I'll explain. So this 2 + 1 dimension is new, and it's also in progress. So all of these have experimental significance in cold atom systems, especially in the case of the hardcore Bose gas, which is also called the Tonks gas, which is in fact equivalent for most purposes to a fermion system in 1 + 1 dimension. So some of these things might sound technical, but when I explain these, it will be quite familiar, I hope. The method arose in early applications in the context of C = 1. So the way we contributed to this game is that this phase space hydrodynamics method. So the classical phase space methods we were familiar with in the context of C = 1, so which corresponded to two-dimensional string theory, and which was applied also to other contexts of string theory like giant gravitons, and also gauge theory, low-dimensional gauge theories like super-Young theory and a 2D torus, which also had some holographic significance in terms of some string theory background. So the plan for the rest of the talk. So hopefully I have been able to tell you a little bit about the why one looks at these systems, and what are roughly the techniques. And now I'll tell you a specific technique. So review of phase space hydrodynamics for large N fermions. And I'll discuss 3 results. So one is how this method that we sort of imported from string theory, it cures the deficiencies of the standard method in which one does large number of particles. So the standard method, which is conventional hydrodynamics, that sort of leads to shock fronts, and the differential equations stop at that time. So our method using phase space rather than coordinate space, that allows us to nicely ride over the shock, and so I'll tell you how that goes. And then once we are able to ride over the shock and go beyond, we see that the system equilibrates to generalized Gibbs ensemble, and surprisingly, this we can see all classically. That's another point I want to emphasize. So Sunil, how am I doing with time?
Well, you have about, let's see, 15, 17 minutes.
Okay, great. Okay, so the universal, and then, so we show that it does equilibrate, and these are systems which are a Fermi gas, so therefore it is an integrable system with infinite number of conserved quantities. So therefore the appropriate ensemble to describe them is this grand canonical ensemble. Grand meaning, this like the super grand canonical ensemble with infinite number of chemical potentials, which I have called generalized Gibbs ensemble. It is called generalized Gibbs ensemble, GGE, and the relaxation exponents from the shape of the confining product. So here are some universal results that I will flash about. So most of these results I will say will be without derivation. Okay, so and then I'll also briefly mention about 2 + 1 dimensions. So we have some ways of applying these things to Landau electrons, and I'll very briefly. So a statement of the problem. So the experiments in a number of ultra cold systems involve the following questions. Suppose we have a system of non-interacting fermions or equivalently infinitely repelling bosons. So this is called a Tonks gas. And in cold atom systems, it is the infinitely repelling bosons which comes more naturally, but it can be shown quite easily in one space dimensions that the infinite repulsion is basically equivalent to Pauli exclusion. So the boson system with infinite repulsion is equivalent to a fermion system. So these are, so what's the experiment? The experiment is that they're kept in a confining potential, perhaps created by some optical lattice, and they're suddenly released from confining potential to free space. Okay, typically free space is modeled by some periodic box, or to define a different confining potential. So like the shape of the confining parameter, like if you have quadratic, then the coefficient of the quadratic changes. So these are examples of quantum quench, and the problem is to find the subsequent quantum evolution of the state of the system if we started from the ground state, let us say, initially, or some other specific state. Okay, so, and what does one look for in the subsequent quantum evolution? One looks for stabilization or the lack of it, relaxation or the onset of chaos, etc. So the exact treatment can be done. It requires finding single particle eigenstates and doing Bogoliubov coefficients. So the oscillators before and the oscillators after, they are related by Bogoliubov coefficients. And the old Fermi C, so in a sudden quench, the wave function doesn't change. So in the post quantum phase, the wave function remains the old Fermi C, but you have to write that old Fermi C in terms of the linear combinations of new eigenstates. It can be done, but it can be done, often it can only be done numerically. Okay, so that's the way of doing it using the exact oscillator methods. Hydrodynamics. Now, even long before we went into the game, people realized that when the number of particles is large, it's natural to try a continuum description in terms of the density. This is the x and t are the usual coordinates. X is the usual coordinate thing of the fermions, and t is of course so times so the density and velocity of these particles. Okay, this is what so fermion density and fermion velocity. Okay, the velocity field and the density field. The evolution of the particle density is assumed to satisfy the usual continuity equation of hydrodynamics. So usual continuity and Euler equation. So this comes from conservation of number of particles, and this comes from the Lagrangian, the force law. Okay, so now the problem is that there are several drawbacks of these equations. One major problem is that there are spurious singularities that appear in this thing, and when there are shock fronts that appear, because what happens is that high density regions move faster. So even if you started from some smooth profile, okay, soon enough, and I'll show you pictures that how shock fronts actually appear. And so in particular, when the shock fronts appear, so the gradient of the density becomes infinity, as you can expect. Okay, and so when that happens, you can see easily that these equations don't work anymore. Now, there have been ad hoc methods of trying to discourage formation of such infinite gradients, in particular by adding some ad hoc terms, but they do not actually solve the problem. The time development beyond the shock cannot be computed reliably from conventional hydrodynamics. Okay. So here's one example in which these dotted lines are the ones that you have found by actual Bogoliubov transformation by exact treatment of the quantum system. That, of course, can be taken to arbitrary times, but the hydrodynamic method gives you these singularities which show up as uncontrolled oscillations after the shock is formed. So the shock forms when this rho of xt for some particular time t becomes completely vertical. Okay, so that is those are the places where del rho del x becomes infinity, and so this is the story. This was the story before we entered the game. So we will solve this problem by using an exact treatment at n equal to infinity, which we had arrived at in the context of c equal to 1. This is the old works on two-dimensional string theory, and I'll tell you how that works. So in fact, even in the two-dimensional string theory context, the conventional hydrodynamics also appeared. Okay, in the works of Das and Jivicki, who treated this problem by collective field theory, but they had the same problems of the shock formation and so on. So even in those days, we used to know that the phase-space hydrodynamics methods avoids these problems. So hydrodynamics in fermion phase space, the way it happens is that so this is a free fermion. So each fermion satisfies a single particle Hamiltonian. And you can describe the system by second quantized fermion fields and its second quantized Hamiltonian and so on. So the fermion field satisfies Dirac-like equation, non-relativistic version of that, basically Schrödinger equation, and a fermion number constraint. Okay, these can be written in terms of this bilinear variable, involving psi dagger and psi, which is called the Wigner phase space distribution operator. So basically, expectation value of this operator in a particular state that approximates the phase space distribution of the fermions. Okay, of course, phase space distribution quantum mechanically cannot be exact because of uncertainty principle. That all is taken care of in the model. And this is the this is the second quantized phase space distribution operator called the Wigner phase space distribution. It satisfies so basically the expectation value of this thing, which I call small u, that satisfies an equation which is pretty much like a usual Poisson bracket evolution of phase space quantities, except that it's not Poisson bracket, it's something that is called Moyal bracket, okay, which only in the h bar going to 0 limit becomes the Poisson bracket. So there's a long story about these things which I can come to in the questions. Okay, and this guy satisfy the small u phase space density satisfies u star u equal to u. So this is almost like, so this also becomes like the usual product. This is star product, some non-commutative object. But we'll be interested, in fact, in the large n limit done in such a way that this star product becomes normal product, h bar goes to 0. And so let's go there. Okay. Now in the large n limit, what we do is that the n going to infinity and h bar goes to 0. This is the limit that we take, so that n h bar becomes 1. Okay. In this limit, everything becomes classical. So the phase space distribution satisfies the Poisson bracket evolution, which is what everybody is familiar with, and u square is equal to u. So this relation, which essentially came from the fermion number constraint, both of these things, and sorry, this came from more from the statistics. Okay, the Pauli exclusion principle. And now in this limit, you can see that Pauli exclusion principle is exact. I mean, it's a sort of obvious. U square equal to u means that there are only two kinds of solutions: u equal to 0 or u equal to 1. So this means that the fermion at any particular phase space point in a cell around it, the fermion, it's either occupied by one fermion or not occupied. Okay, so that's the thing, that is 0 or 1. In a bosonic system, it need not be 0 or 1. It could be 0, 1, 2, 3, anything. So this is what this is what the hallmark of the fermion system is. So as a result, you can characterize all solutions of this u square equal to u in terms of droplets. These are called droplets, and you black out the regions in which u is equal to 1, and it's white where u is equal to this thing 0. And so you can have smooth droplets like this, or you can have this kinky droplets in which what happens is that if you draw a vertical parallel to the p-axis, so this is a phase space, so this is x and p parallel to the p-axis, then it cuts at multiple points. Whenever that happens, okay, you have a shock. Okay, that's easy to see. And in this thing, therefore, the conventional hydrodynamics develops. So I have some, I have some sort of. Okay, never mind. I'll come back to this thing if there's time. Okay. So what's my main point here is that this equation, okay, where the real space density develops a shock, this equation does not. Okay, this equation does not, and because it's just a fold in terms of the phase space of the hydrodynamics. You see that there are no non-smooth behaviors here. Okay, if you follow the fluid particles, okay, they are all doing their own thing nicely, and only when you go to the coordinate space density description that it develops a shock there. So if there's so there are some details here which I don't have time to go into. But let me tell you the results.
Sorry to interrupt. You have 5 minutes.
Yeah. So I think I can do the results. So now the point is that this is the way we get it. So in terms of the usual phase space density using the conventional treatment at this time t equal to some particular time, we would have had infinite gradient of the real space density, and the result would have stopped. But when we discuss in terms of phase space hydrodynamics, we can derive the real space hydrodynamics, real space density from there, and you can see this red thing. It actually has infinite gradient here, but we can go beyond that, and there is no problem with this. So we actually find that without any ad hoc corrections to the conventional hydrodynamics, we just go one dimension up in terms of phase space hydrodynamics, and we find that we can do this. So and yeah, so these are some details of how we do these things. But let me tell you the interesting stuff. Okay, which we can say qualitatively. Okay, let us say that I have some phase space droplet like this to begin with. Okay, this is a periodic box, and I start with some phase space droplet which is this way. So there's a little bump here, and you see the point is that in phase space these droplets evolve as if each fluid particle, each point is evolving according to its own equation of motion. Okay. Now, this is a free particle. This is an example of a free particle. So these guys on the top, they have higher momenta because they are higher up. So therefore, they go faster, okay, than things below. So soon enough, it sort of develops a fold here, okay, and then the fold touches the box, and soon it becomes like fingers, okay, and filaments. And you wait for a long time. So these filaments just start filling up this space, and soon enough there's a average density, okay, which is like u equal to 1 here, and it's fully occupied, and it's 0 here. But in between here, it interpolates from 0 to 1. And this is precisely what the thermal ensemble says, that if you take a thermal ensemble or more like the GG ensemble, then so this is the real picture. This is the picture. Because of the filaments and the fragments, the fingers, you have these guys developing, and it's actually so these are the mathematics of that. It actually reproduces the GG completely. And now, so here's the proof that it actually gives you the thing. So, but the main picture that you should carry home is this. Okay, and this can be developed. This can be described classically. So each point here, okay, classically evolves as a free particle. X is equal to x naught plus pt, and so you can just carry that through. Okay, so now. Yeah, so here's an example of a graph in which you apply this method to show that, like, this is a certain moment of the density, and in this periodic box theta, and it equilibrates to a value which is not given by the Gibbs ensemble, but it's given by the generalized Gibbs ensemble, according to how you should treat these things in and here are some results about I think I'm more or less over time. So here are some exponents that we actually got excuse me, from the shape of the potential, which is x to the power 2m. You get this power law exponent, and if you go from a box potential to a circle potential, bigger periodic box, then this is the way it is, and so on. So there we got some universal results about the power law exponents, and the way we did that was, so there is some amount of mathematics that you have to do, but this is all done by classical evolution of each of these particles. And so here we have embarked on some 2+1 dimensional works with Satya Majumdar and collaborators, and Manas Kulkarni and Takeshi and and myself. And these are lambda fermions, which are so these are fermions this is a Fermi gas in 2+1 dimensional systems, which are rotating, and the rotation, the angular velocity is is tied to the magnetic field. So it's close to the value of the magnetic field. It's a small departure from there. So anyway, under specific circumstances, 2+1 dimensional fermions they have a lot of properties which are close to 1+1 dimensional fermions, and our methods of thermalization can actually be applied there. And this is my final conclusion. So I studied quantum quench in 1+1 and 2 dimensional Fermi gas. The larger limit leads to phase space hydrodynamics, droplets, which is exact and does not suffer from spurious singularities. I should have said here that it's exact and classical. So this allows study of long-term dynamics approach to equilibrium. We described how universal relaxation rates can be obtained, and there are ongoing works like how one, so this was at n equal to infinity. So how 1/n corrections can be done. So there was this phenomenon called double scaling in the context of 2-dimensional string theory, and 2+1 dimensional modulus, you can do more things about it. And that's what we are discussing as well. Thank you.
Thank you very much, Gautam. So let's unmute and clap. So I don't see any questions in the chat box, but I see one hand raised. Ajit, would you like to unmute and ask your question?
Yeah, hi, Gautam. Thanks for a very nice talk. I have this question that for conventional hydrodynamics, the shock fronts are physical. They're not spurious. In the ideal fluid limit, the discontinuities actually are real. You get discontinuities to the level of microscopic length scales.
So okay, so there are there are experiments with this Tonks gas, where you can do the experimental evolution beyond the times where these conventional hydrodynamics shock fronts appear, and you can you can compare that with the Bogoliubov transformation method that you get from exact n treatments from the quantum mechanics, and they agree. However, the conventional hydrodynamics treatment that does not agree. So the shock that is shown up by the conventional hydrodynamics, they are definitely spurious, because the exact treatment goes beyond that, and that also agrees with experimental things. So what you were saying here is perhaps something different, but in these examples from the ultra cold atom systems, especially the references that I have mentioned, like by Damsky and other experimental people, we can discuss this. I'd like to learn about this stuff, but certainly it can be extended beyond this so-called shock formation, which is predicted by conventional hydrodynamics. That I'm sure.
Okay.
Hello.
Yeah. Are there other questions? Okay, if not, I have one brief question. Gautam, on slide 17, you had drawn this nice picture of two types of like droplets, yes. One being convex and the other having some concave part. And then you said something like the vertical line intersects twice. Of course, it intersects, I mean, it goes right through in the left one, right? So twice.
The vertical sign, oh, did I say twice? I should have said more than twice.
More than twice. Okay. Yeah. So it intersects the boundary more than twice.
Yeah. So this story you probably already know from the sequel to one thing is that this is basically, if it intersects twice, then you call those intersection points P minus and P plus. Then the density and the velocity, this density field, the real space density field, is given by P plus minus P minus, and the real space velocity field that is given by P plus plus P minus. And whatever you could do with phase space methods, you can also do with the real space methods. But soon enough, such things appear, and then there is no characterization in terms of this quadratic. So this is something that that is called quadratic profile, and this is what is more than that. And then the thing between connection between phase space hydrodynamics and conventional hydrodynamics fails. And of course, the phase space hydrodynamics method that continues to work, because it's very simple. It's just this, and it in fact follows, these equations follow by saying that each fluid point satisfies its own equation of motion.
Okay.
Yeah.
Okay, thank you. Are there any other questions? If not, then let's thank Gautam again. So thank you very much, and thank you for keeping within time. So you can now unshare your screen, and I'll invite the next speaker, that is Alok Laddha. His title is Geometry of Scattering Amplitudes. So Alok, hi, I can see you now.
Yeah.
Please share your screen, and your talk will be 35 minutes. I'll warn you at 30 minutes.
Okay. Thanks, Sunil. Yeah. So let me know when to start.
Oh, you can start.
I can start? Okay. So I would first of all like to thank the organizers for arranging this really remarkable meeting and also inviting me to speak here. So my talk is going to be about some recent developments in the analysis of S-matrix theory, and broadly known as it's called the amplitude hedron program. So hopefully I'll be able to give you some flavor of some of the recent developments in the subject. So maybe first I'll start with some motivations. As we know, scattering amplitudes are fundamental objects in quantum field theory, but in many ways they are elusive. And even now, even in perturbation theory, they continue to reveal interesting new structures. In fact, there's a famous movie called The Matrix, in which there is this interesting line that nobody can be told what an S-matrix is. You have to see it for yourself. And we know in quantum field theory, this statement is true in many ways. For example, I mean, one definition of quantum S-matrix is, in perturbation theory is via Feynman diagram. So we just take a theory and we want to compute n to m particle scattering, we sum over all the Feynman diagrams. However, Feynman diagrams, I mean, by now it is becoming clear that they obscure the simplicity, in many cases, some symmetries which are inherent in the scattering amplitudes. And the most well-known example of this kind of obscure the limitations of Feynman diagram in certain sense is when we compute what are called maximal helicity violating amplitudes in say 4 Yang-Mills, in pure Yang-Mills theory in 4 dimensions. And it is known that this amplitude for any number of particles can be written in a compact rational form as a function of momenta and polarization. But we know from Feynman diagram, this would be difficult to do because even to compute 9 gluon amplitude, you need like of the order of 50,000 odd diagrams. So clearly something is lacking if you try to compute this amplitude from Feynman diagram perspective, but from different techniques, you get very nice results in like for an arbitrary number of particles. I mean, complete result for arbitrary number of particles. Then, of course, S-matrix is a non-shell object, and so it's gauge invariant. But when we do compute S-matrix in perturbation theory using Feynman diagrams or Lagrangian methods, we have to start with fields. And as we know that when we introduce fields, we have these complications with, gauge and off-shell computations, and they sometimes introduce unnecessary complications. So in fact, this is the reason why many of the computations in Yang-Mills theory are very complicated if you use Feynman techniques as opposed to some of the other techniques which have been developed recently. And even leaving aside the question of efficiency, we can still ask, I mean, how much do Feynman techniques tell us about the definition of an S-matrix? So, but to answer this question, we really need to first, have a kind of a definition of S-matrix in mind. So, in other words, we have to look at the core postulates which define, which any definition of S-matrix has to satisfy. And these postulates, as we all know, have been known from the 60s. And the core postulates are, of course, unitarity. And if you're in flat space-time, Poincare invariance, there is crossing symmetry, and a more subtle postulate, which is called maximal analyticity, which is kind of at the heart of the S-matrix, old S-matrix program. So in essence, this postulate tells us that if you consider the full complex plane spanned by Mandelstam invariants, the only singularities of the S-matrix are those which are consistent with unitarity and causality, or in other words, locality. But so if you know the singularities, then you know a lot about the S-matrix. But the problem is that the singularities of even a perturbative S-matrix are very hard to classify. So in fact, the full so even for scalar field theories, if you do perturbation theory of scalar fields, then the full structure of singularities, where are the branch cuts, where are the poles, etc., is kind of complicated, and is kind of encapsulated in this famous line in the old QFT book. Where the studies of complex singularities in scattering amplitude is actually quite complex. So this is the core question that we would like to have an answer to eventually, that how do we classify functions in the Mandelstam space which are Lorentz invariant, unitary, and represent analytic S-matrix. So that it has the only singularities it has are consistent with local and causal quantum field theory. So this is just to continue with the Feynman limitation of the, in some sense, limitation of the Feynman diagram as a representation of the S-matrix. So as we already discussed, sometimes they obscure this simplicity of many amplitudes because they don't respect the symmetry which may be inherent in the scattering amplitude. So in the case of this so-called maximal helicity violating amplitudes in gluons, there is this symmetry which is now well understood called the Yangian. And the symmetry you do not see at the level of individual Feynman diagrams, but only say when you sum all the diagrams and get the final result. And as we discussed about, they rely on structures which one could consider auxiliary from the perspective of S-matrix. So because the S-matrix only depends on the particle content of the theory. So the fact that we want to maintain locality at every step of the computation it could be kind of an unnecessary hindrance in understanding the S-matrix. And then there are deeper structures that people are now understanding. For example, there are so-called double copy relations which relate amplitude in one theory, like say gauge theory, to the amplitude in gravity. And again, at the level of Feynman diagrams, these relations look very mysterious. So we can ask, okay, is there a representation of scattering amplitude in which, for example, the simplicity of gluon amplitude, MHV gluon amplitude is manifest? And indeed there is one, and this is called what are called Bcfw recursion relations, where you the idea is that you don't worry about locality, but you can construct any arbitrary endpoint gluon amplitude precisely from on-shell 3-point amplitude, but where you take the external momenta to be allow external momenta to be complex. Now, it turns out that in these computations of recursion relation, locality is not manifest at every step, but only but on-shellness is manifest. So you never go off-shell in the computation. But at intermediate step, you will see some non-local terms emerging in the computation. But at the end of the day, the answer is local. So kind of this recursion relation tell us that maybe locality is not a fundamental postulate, but a consequence of some deeper principle. And this was a question which was asked by Hodges almost 10 years back, which started this whole program that I will be trying to describe in some detail today. And then there are these other symmetries in Yang-Mills theory, for example, which are called color kinematics duality. And these are made manifest in a different representation, which are called BCJ representation. But again, these BCJ diagrams are also not, if you look at individual diagrams in this representation, they are also not manifestly local. So in fact, these diagrams really, I mean, this representation really reveals something truly deep about gauge theories, in the sense that if you write S matrix of Yang-Mills theory in this representation, then there is a direct prescription to sort of square the amplitude so that you get a perturbative gravity amplitude. So it's somehow tell us that theories which may look very different from Lagrangian perspective may be deeply related to each other at the level of S matrix. Finally, there are representations which are inspired from string theory, and they really, in some sense, from ordinary QFT perspective, look exotic because they are defined on some auxiliary space, like for example, world sheet. In this representation, scattering amplitudes are result of integrations of some some functions or forms on some exotic space, what is called moduli space of Riemann sphere. Neither locality nor unitarity is manifest in the formula, but in the final result is local and unitary. So and the reason that you get the final result, which is unitary and local, is because of the geometry of the space on which these formulas are written. So perhaps this representation is telling us that even unitarity is a consequence of some deeper principle rather than a postulate. And okay, there are some other representation that I will skip for now. So just in a nutshell, I mean, this kind of a long-winded motivation that we don't know what a perturbative S matrix really structurally is, but we now have many representations, BCJ, CHY, and many others. And one extreme example of this ambiguity is, of course, ADS CFT, where ADS amplitude is represented as a CFT correlation function. And properties manifest in one representation many times become corollaries in the other representation. So the question we were initially asking, that what is the structural definition of S matrix, maybe we could rephrase the question that, is there a framework of S matrix in which all these disparate revelations can be unified? And if there is, what are the fundamental postulates on which this definition is based? So this is kind of a long aim of the so-called amplituhedron, or what is called positive geometries program, is to sort of encompass different representations of the S matrix. And I think even at this stage of development, it seems to offer some interesting new insights on what an S matrix, perturbative S matrix is. So here in this talk, I'm going to really focus on just scalar field, like simple scalar field theories, and going to show that actually there is so we are going to look at like phi to the p interaction, where phi is a scalar field. And we are going to show that there are just some simple geometric objects which are called polytopes. These are, you can think of them as higher dimensional generalization of just ordinary polygons. I mean, they have some names, accordia, etc., which naturally, their volumes in some sense just give you amplitudes, tree-level amplitude and integrants for one loop amplitude. And these are really simple to construct, and hopefully I will be able to at least give you a flavor of what these objects are in this talk. So before I start with the main talk, let me just put some small disclaimer that we will work with what are called color ordered amplitudes. I think in this audience doesn't need an introduction to color ordered amplitudes because they are so common in QCD. But essentially what we do is we fix ordering of particles on a circle once and for all. And from the perspective of Feynman diagram, we will only sum over graphs which preserve this ordering. So of course, in Yang-Mills theory, full amplitude can be written in terms of this color ordered amplitude, and each of these color ordered amplitude is planar in the sense of the graphs that you draw to compute them are planar. And the main reason for doing this in this talk is because the ideas that I'm going to explain are best developed for this class of color ordered or planar amplitudes. But I just want to sort of just say that this planar does not mean large n or anything. It's just the color ordering. And although just for simplicity, because of lack of time, we restrict ourselves to massless particles, as the formulation is dimension independent. I mean, you can write these S matrices from this formulation in sort of any dimension. So this in itself is not a severe restriction, and the results easily generalize to a single massive scalar field. Although there are the things become much more complicated if you have multiple fields, and there are some interesting developments in that side. But this is something we will not go into in this talk. So roughly my plan of my talk is the following: that I first give you the entire construction of this amplitude hedron program for tree level amplitudes, scalar field amplitudes at tree level, and then if time permits, I will tell you how precisely the same structures actually generalize at the level of one loop amplitudes. So because we don't want to start from any core postulates, we don't really have much to work with. So we start with some very raw structure, and then the only structure we are provided with is basically space of Mandelstam invariance. So if you are only looking at this color ordered of planar tree amplitudes, then you can show that this space is spanned by not all Mandelstam invariants, but only those which are of the following sort. So if you consider, because we have an ordering of the particles, so we know that, for example, I can be less than j, then for each I less than j, we can define these variables, which are sort of generalization of Mandelstam invariants. And this, it can be shown that this form a nice basis for this kinematic space of Mandelstams, if you are only interested in computing color ordered amplitudes. So, but now these things have nice geometrical meaning, because what we can do is we can think of a polygon, some abstract polygon, nothing to do with physics right now, which is formed by n vertices, where the vertices are labeled in clockwise direction. And you can think of xij being like a chord which joins the vertex I to vertex j. Now, once you have these xij's, you can start playing some interesting games. Like, for example, you can look at any set of xij's which dissect this abstract polygon into cells, like say triangles, quadrilaterals, or any other n-gon. And it turns out, and this is something that mathematicians have discovered, and I mean actually continue to discover even now, that if you take the set of such dissections, then you can use them to construct some interesting abstract polytopes. Again, nothing so far to do with physics, just some combinatorial objects. But as you will see that these abstract polytopes are the seeds which naturally end up generating S-matrix for scalar field theories. So first, let me give you an example of what these polytopes are. Okay, so this is the first example. So suppose you take a pentagon to start with. So you have say 5 particles, and you start with a dissection where you dissect this pentagon into triangles. So you have say, for example, you need 2 diagonals. Now the polytope, this combinatorial polytope that you construct is very easy to, it's very easy to construct, that you start flipping these diagonals. So you, for example, if you go towards the right, then you flip the diagonal, the diagonal on the right, and then you keep flipping one by one, and you can easily check that in the end you come back to the same configuration that you started with, and as a result you get a combinatorial pentagon. So that just shouldn't confuse this pentagon with the pentagon we started with. The first pentagon was some pentagon where we just put particles at the vertices, but because of this combinatorics of these dissections, we end up with an interesting combinatorial polytope. And this polytope has been known in mathematics for a long time. It's called the associahedron. But so this is one example of an associahedron in 2 dimensions, which is itself a pentagon. But this construction that we start with the dissection, in this case a triangulation, and then we end up with a polytope, is actually much more general. Although the mathematics definition is more intricate, I'll give you one example. So instead of looking at triangulation, suppose you look at quadrangulation. So let's say that you have a hexagon to start with. So you have 6 particles, and you break it into 2 quadrilaterals. So you just join, like, put one chord here, one fold. Then this math definition of combinatorial polytope tells us that you are not allowed to do 2 flip. You're not allowed to. You are only allowed to do a flip where this 1,4 goes into 3,6. So you could have thought that, okay, there are 3 ways to break this hexagon into quadrilaterals: by 1,4, by 3,6, and by 2,5. But the combinatorial polytope definition is such that 2,5 is somehow not allowed, only 3,6 is allowed. So as a result, you get a 1-dimensional combinatorial polytope, which is labeled by 2 vertices, and each vertex corresponds to one quadrangulation of the hexagon that you started with. So and these objects, these general polytopes, are called accordiahedra. If you say, that is, if you start with a dissection Q, which is not, for example, triangulation, but anything else, like in this case quadrangulation, then the objects you get are called accordiahedra. And if you start with triangulation, they are called associahedra. So here is another example of this accordiahedra. If you start with, say, octagon, and you break it into 3 quadrilaterals, and if you start with 1,4, 1,6 as your initial dissection, then you end up with a combinatorial pentagon here, if you follow the rules that the mathematicians kind of gave us. But so these are just some examples of this combinatorial polytope. Again, so far nothing at all to do with physics. But let me just summarize some of the properties based on this example. So basically, for any dissection Q, that is, you break them into triangles or quadrilaterals or anything else for that matter, we get precisely one combinatorial polytope. And the interesting thing is that if Q is a triangulation, then the corresponding polytope is unique in the sense that in this case of the triangulation, you could have started from any vertex here, and you would always end up with the same combinatorial polytope, whether you start from here and you start flipping, or you start from here and you start flipping. So you don't there's only one polytope that you could construct. Unlike here, where because you start from 1, 4, you get 3, 6. But if you follow the math definition, then if you start from 2, 5, then you would get you would get 1, 4 as extra vertex. So if Q is a triangulation, then the corresponding polytope is unique and is independent of the choice of the dissection that you start with. And this is called associahedron. These polytopes are called associahedra. And if Q is anything else than a triangulation, then somehow the polytope you construct retains the memory of the dissection that you start with. So if you start with a different quadrangulation, you get different polytopes of the same dimension. And there's an interesting happy fact about these polytopes, that the dimension of these polytopes, which are built out of say triangulation, quadrangulation, pigulation, I mean where P is 3, 4, etc., is same as the number of propagators in an n particle amplitude, which has 5 to the p interaction, which is not very hard to see actually. So associahedra, for example, has n minus 3. If you take n gone and you construct this associahedra from triangulation, the dimension of the polytope is n minus 3, and that's precisely the number of propagators you need in an n particle Feynman diagram, which if you only had cubic vertices. And now here is the intuitive thing which will help us when we go to the physics content from here, is that each boundary of this polytope, you can think of this as some propagator going on shell in a Feynman diagram. So just to, if you look at this one, then you can think of this 1, 4, this is a boundary which is characterized by a quadrangulation given by 1, 4. You can think of this as x14 Mandelstam variable going to 0. This is just for intuition, just to keep a kind of a picture in mind, as it will be useful later. And okay, we can do some very simple dimension counting. So this space of Mandelstams, which are coordinatized by these xij's really, it has this dimension for n particles, n into n minus 3 by 2. And this associahedra, as we saw, has a dimension n minus 3. So these polytopes are smaller objects than, of course, in the kinematic space. And similarly, if you take, for example, quadrangulation and you construct the polytope, then the dimension is even smaller. If for n particle, it's n minus 4 by 2. So as you change the dissection topology, you start getting smaller and smaller dimensional polytopes. Again, these are some combinatorial polytopes. So far, they don't have anything to do with the kinematic space, but in a moment, we will see how they, we can realize them as concrete geometric objects inside the kinematic space. So this is what we do now. So in fact, this is sort of one of the most important ideas which have been developed in the field, that these combinatorial polytopes are actually just sitting in the, if you just look at the positive quadrant of the kinematic space, where all the xij's are either positive or 0, then this combinatorial polytope are actually just sitting there. All we have to do is kind of discover them. And this was done by 4 physicists, Arkan, Ahmed, Bai, He, and Yan. And then it was followed by a number of mathematicians, especially these 4 gentlemen that I've listed here. So basically because these polytopes are smaller dimension, of course, we need equations to locate them in the kinematic space. And so I'll just give you a flavor of how to locate these polytopes. So kinematic space, of course, some simple Euclidean space, with each axis labeled by xij's. And of course, you may think that, okay, if you take a polytope like a pentagon, I can draw it in a Euclidean space like plane in many ways, infinitely many ways. However, as we do not have any mass scale in the theory, we are looking at massless particles, we can think of this, this Euclidean space as some projective space. Okay, just some technicality, maybe not very important, but a space which has no scale in certain sense. Now, it turns out that if we think of this space as not as a Euclidean space, but as a projective space, then all of these polytopes, associahedra, quadrahedra, etc., they have a unique realization in this projective space due to a distinct relationship they share with some algebra, some abstract algebras, which are called cluster algebra. So in some sense, these combinatorial polytopes themselves tell us which realization one should get if you don't put any extra input in the kinematic space. And it turns out that precisely these realizations produce amplitude, which is quite, in my opinion, a striking fact. So all the hard work in finding such realization actually was done by Arkan, Ahmed, Bai, He, and Yan, and then followed by a group of mathematicians. So let me just give you, the analysis is of course a bit technical, but let me tell you the final result, which is extremely simple to understand. So we want to find some equations which we can use to find some, realize these polytopes in this projective or Euclidean space. So, okay, we first start with a very simple relation of Mandelstam invariants Sij with Xi. So Sij are our usual Mandelstam variables, and you can show that they can be written in terms of these Xij variables by the simple linear relationship. Now, okay, here is the equations we need to realize these polytopes. So suppose Q is some triangulation which generates, say, this associahedron of n gone. So let me just call it An. You take that triangulation and you consider a triangulation that you obtained by rotating Q counterclockwise. So you got a new triangulation, and then you just write the following constraint. You freeze all the Mandelstams where ij's do not belong to this counterclockwise triangulation. So okay, again, maybe not the details are not important, but I just wanted to convey the message how easy it is to realize these polytopes. This is the algorithm that one can just use. So, and intuitively, basically what these constraints do is freeze all the Mandelstam variables, which, for example, never occur as poles in, say, phi cube amplitude. Here, I'm talking about phi cube amplitude because we are talking about the associahedra which came from triangulation. And the same ideas hold if you look at, for example, accordiahedra which come from quadrangulation. Then, you will be freezing variables which never occur in a phi 4 amplitude, for example. And so we can repeat this procedure for any dissection and locate this accordiahedra in the kinematic space. So now we have some. Just from some combinatorics, we got some shapes in the kinematic space. I mean, we haven't really put any principle so far in the game. So just to give you an example of what these realizations are, if you take a one-dimensional associahedra, which is just a line with two vertices, you can realize it as a 45-degree line in the x13, x24 plane in the kinematic space. So it's really this. The fact that you got a 45-degree line as opposed to some other line is what the this math results of the combinatoric polytope told us. So they gave us these distinct realizations which have this particular slope. Just to give you another example, if you take a two-dimensional associahedra which comes from the 5-gon, that combinatorial polytope that we saw above, it has this precise realization where, for example, the face, this bottom face and the top face are parallel, and the two vertical faces are parallel, and there is one non-vertical face. So there is some particular shape that you get for this associahedra. So these are the realizations of these combinatorial polytopes in the kinematic space. And in fact, there are some nice properties that these polytopes have. So for example, because the accordiahedra of smaller dimension, you can show that you can always like embed these polytopes inside the associahedron, because associahedron is a n-3 dimension, which is the largest dimension polytope we can construct here. So kind of this last property shows that the associahedra, like the master polytope, if you know them, as we will see, we kind of start getting information about amplitudes for generic scalar field theories. Okay, so this is just a summary of what we saw about that. Starting with any dissection of a polygon, we got some concrete geometrical objects in the positive region of the kinematic space. And now we are almost there. Now we want to find the amplitudes from here. So this is just an example of a one-dimensional accordiahedra that we saw above, where we split the hexagon into triangulation. So there was a one-dimensional combinator of the polytope. It actually is realized inside a three-dimensional associahedron in nice way. Okay, and now here is a nice theorem that mathematicians kind of gave us, which basically produce amplitudes for us now very easily. So once we have this accordiahedra which are embedded in this kinematic space, they actually define a volume measure in the full space, and you can use them to compute volumes of some, as we will see, some geometric shapes which produce directly the amplitude for different theories. So given these geometric shapes we have, there's a natural measure that one can induce on the full kinematic space, and we can use it to compute certain volumes which produce the amplitude. So let me just give you an example. So suppose I start with this two-dimensional associahedron, which we realized in this x14, x13 space. Then we can look at a polytope which is dual to it, only in this sense that each vertex of the polytope is sitting on the edge of the original associahedron, etc. Now this associahedron which is realized, the black thing, gave us a measure with which we can compute volume of this red polytope. So when we do that, the volume of this red polytope actually precisely produces the phi cube amplitude for a ordered phi particle. Sorry, this should be P1 to P5, I apologize. So it directly produces the scattering amplitude in the phi cube theory for phi particles. And now the same idea actually quite strikingly holds for any theory. So you start with, for example, you will look at like phi to the P theory. Then you start with all the accordiahedra where ACQ, where these dissections dissect your n-gon into p cells. Like if you start with 5 to the 4th theory, then look at all the dissections which split the polygon into quadrilaterals, and you compute volume of each of these associated accordiahedra in the same way, like the dual of the accordiahedra in the same way, and add them with certain weights. So, and it turns out actually that for each p and n, for each 5 to the p and each n particle, there is a unique set of these weights, such that the above sum gives the amplitude for 5 to the p, for the massless 5 to the p theory, the tree-level amplitude. So this is the main idea, that somehow from just starting from very basic combinatorics on a very boring space, kinematic space, which had no structure, we are able to get scattering amplitudes. But now we may wonder why it worked, because we obtained in the end some unitary and local amplitudes, and it looks like we didn't put much input to get these amplitudes. But actually locality and unitarity emerged due to some striking properties of these polytopes. And easy to understand the following way, that if we suppose zoom in towards any of their boundaries, we get the polytopes at the same accordiahedra of lower dimensions again. So what I mean by this is the following, that in general, if you take a family of polytopes, for example, say you take a line in 1D, you take a pentagon in 2D, and in 3D you take a polytope which has one face which is an hexagon. So that means that if we zoom in onto this face of the three-dimensional polytope, it is not in the same family of polytope, because in 2 dimension, this family only had a pentagon. But this never happens in the accordiahedra. So every time we have a higher dimensional accordiahedron, we go to the boundary, we always end up with the accordiahedra which in that family which was in the lower dimension. And as some intuition that I said in the beginning, that as each boundary kind of corresponds to placing some of the propagators on shell, this tells you why the amplitude factorizes into the lower point amplitude. And this factorization is of course at tree level simply a statement of unitarity. So unitarity kind of emerged nicely simply because of the geometry of this polytope. So actually just a combinatorics of the polytope. And then we can ask, okay, where did locality emerge from? Why do we get only simple poles in the amplitude? Now the point is that this projective measure that was induced by this accordiahedra on the kinematic space. So there is a natural measure, as we discussed, that this accordiahedra give us on the kinematic space. This measure is such that it has simple poles on and only on the boundaries of the polytope. So on all the boundaries of this polytope, it has a simple pole, but it is only simple poles there, and one can show that this is the reason why we got locality from this polytope. So and actually, okay, one could think this would be okay, it's all tree level, but it turns out that this entire picture actually holds at the level of one loop integrand. So Sunil, how much time I have? If you
yeah, so I was about to just give you the 5-minute warning, so you have basically 5.5 minutes.
Okay, thank you. Yeah, so I will go a bit fast, but the ideas are really the same. The polytopes are more intricate and in some sense a little bit more interesting also. So let me just so this work for the 5-cube theory, one loop integrand work was done by Arkani, Hamad, Hay, Salvatore, and Thomas, and for 5-4 theory it was done by a student here, Brunmai, and myself. So now, okay, so I'll just give you a rough flavor of how the whole thing goes in the one loop case. The idea is the same, but some structures kind of differ. So for example, first is the kinematic space. So of course, we expect that the kinematic space for loop amplitudes will not be the same for tree amplitude, because we need some loop momenta also. And indeed, that's what happens. So this kinematic space that if you want to construct for the sort of so-called planar or color ordered amplitude, they will of course have these Xij variables, which are related to the external momenta, but they also have some variable that label loop momenta and also in fact TED poles. So let me just roughly label these extra labels as Y and Y tilde. Now it turns out that just as for the tree level kinematic space, where we could think of Xij as a chord of a n-gon, all these variables of the loop momenta kinematic space can be thought of as chords of a 2n-gon, but this 2n-gon is special. It has some kind of a hole at the center, which kind of should remind us of a loop, computing the loop diagram. So just to give an example of, suppose you have 3 particles, then you draw a 6-gon. So like basically you draw a 6-gon where you have 1, 2, 3 labeling 3 particles and label them again. And then you break this sort of hexagon with a hole at the center into triangles. I mean, shapes which have topology of triangle. So you have one triangle here, one triangle here, one triangle here, and one triangle here. These triangles are not linear triangles, and because of this reason, this is called pseudo triangulation as opposed to triangulation. So anyway, but this is the upshot that we can realize the full one loop kinematic space geometrically as chords of this 2n1, this abstract. Again, this is all very abstract and it wouldn't be very interesting if it didn't have much to do with physics for us. So the planar kinematic space is parameterized by these internal chords. And now you remember that in the tree level case, the space was parameterized by chords of the n-gon, and combinatorially the associahedron was some polytope we got from triangulation of the n-gon. So as we now saw that the one loop kinematic space can be understood in terms of dissection of the 2n-gon, and it indeed turns out that if there are combinatorial polytopes, you can construct in exactly the same way that we construct associahedron from this so-called pseudo triangulations. And this gives us polytopes. These are known to mathematicians for last few years. They are called type D. I mean, the name is not very important. A type D cluster polytope. And it turns out again that if you compute volume of this dual of these polytopes in the same way, they give us integral for phi cube one loop amplitude. So just to give an example of one of these combinatorial polytope, it looks like this. We have two particles. So you have 4 gon because you have to take 2n gon, and you get a square as a combinatorial polytope. And if you draw the dual of this and then some measure that you get in the same way, the same principle, we get the integral for the one loop. Okay, so I will skip this. And interestingly, it turns out that mathematicians stopped at the cluster polytope. I mean, this polytope I just discussed about. But since we have more motivation from physics, we could ask if there are generalizations of accordiahedra in the case where you have this annulus and from the combinatorics of these dissections. And indeed, it turns out there are. And they produce amplitudes for one loop integrals for phi to the p theory. So that's the upshot. So just one example of a new polytope we found in this process, which were not discovered before. So this is a polytope that you get out of pseudo quadrangulation of these 2n-gons. So, every cell is a quadrilateral as opposed to a triangle, and you get this kind of nice hexagon. If you draw a dual of this, its volume gives us integrand for a 4.5 to the 4 T level at color ordered amplitude. Okay, so I will just end with some conclusion now. So although I just briefly told you about this quartic interaction in the last slide, actually we believe at least that this can generalize to other monomer interactions also. Okay, and now let me just skip to this one. So there are, we could still wonder if it's still at the level of integrand. Is there anything interesting we can say about the integrated amplitude for these theories? And indeed, one way to ask this question is if you can classify what are called Landau singularities of the S matrix using the geometry of the polytopes. So these are singularity of the actual S matrix, not of the integrand. And if you could somehow say something about the singularity structure, we would have made a lot of progress in sort of unraveling the S matrix. And indeed, I apologize, this should be 4. For n equal to 4 super Young-Mills, there is already a lot of progress in this direction, in the sense that singularities which are physical are distinguished from singularities which are spurious by the geometry of these polytopes. And we also see that for scalar field theories, what are called bubble and triangle singularities, which are physical, they are classified in terms of boundaries of polytopes, and singularities which are not physical lie outside the polytope. So so it's a kind of polytope naturally tells you which singularities are physical and which are not. So just to mention my collaborators, so this many of the results that I said were done in collaboration with work with Anish and Sujoy, who are PhD students. Sujoy is in IMSc, Anish is in CMI. Pinakim and Ranjan are postdocs in different places. And most of this work was done with Brunmai, who was an undergraduate in CMI and now just joined PhD in US earlier this year. And thank you. Sorry for going over time. Thank you for listening.
Thank you very much. You actually did not go over time.
Oh, okay.
Thank you for not going over time. So are there questions? So there aren't any in the chat, and I don't see any hands raised. Please raise a hand. Yeah, I see a hand. Namit, please unmute yourself and ask the question.
Alok,
Yeah.
Could you say a little bit about when you have multiple scales involved? Is there some better understanding?
Yeah. There is some understanding. Yeah, I can say something, but it's still under development. So one understanding is, suppose you have one massless and one massive field, for example, and if you have, for example, only say cubic coupling. So if you have Yukawa type coupling. So let me say phi1 is a massless field, phi2 is a massive field, and suppose we just consider coupling which is phi1 cube and phi1 square phi2.
Okay.
Then it turns out that for this we get the combinatorial polytope is actually a 10-gon, and this combinatorial polytope cannot be convexly realized in a single kinematic space, but it can be realized in a two sheeted, I mean, if you put two kinematic, like two copies of kinematic space, then you can realize it as like a double sheeted kinematic space. Now, the interesting thing is that if you take large mass limit, then these polytopes kind of run off to infinity in some sense, these new polytopes, and they degenerate into like a lower dimensional polytope, like one dimensional, or if you started with a two-dimensional polytope for this massive theory and you took large mass limit, you get a one-dimensional polytope, which precisely produced the amplitude for a theory if you had integrated out 5P.
Okay.
Yeah.
Okay.
So
that's what I. And one more small thing. So is it also capable of capturing the resonances which actually lie on the?
No, that's a very good question. No, actually, I don't think there's any answer to this, and actually, this is the reason why also study of Landau singularities, etc., is going to be useful. But I don't know if in super Yang-Mills people have understood anything about these other poles like resonances, but in ordinary scalar field theories, I think there is no understanding so far.
And just one last thing, Sunil.
Yes.
When you say triangle singularities towards the end, you said you are able.
Yeah.
Does that also include the so-called anomalous thresholds? That
Yeah. That's the interesting part. So so the point is that the all the thresholds, anomalous thresholds which are on the physical sheet, they are in the faces of the polytope. But if you have an anomalous threshold which is not, it turns out, at least for the example we have studied, it lies outside the polytope. So there is some potential that it can distinguish between anomalous thresholds which contribute to the on the principal sheet and those which do not. I mean, of course, as you know, for massless theories, the singularities solution to Landau equations analysis is already more complicated. It's more subtle. I mean, unlike in the massive case where it is known that only those singularities which are in the on the physical sheet contribute to the amplitude in the end. And so the anomalous thresholds are generically not in the physical sheet for a massive theory, just a single massive scalar field theory. But that is not true for massless theory. I mean, you can have anomalous thresholds here which are on the physical sheet also, and we find them here.
Thanks.
Yeah, thank you.
Okay, thanks, Namit. Now Debashish has a question. Debashish, please unmute and ask.
Hi, Alok. Can you hear me?
Yes.
Nice talk. I'm listening sort of for the second time, so it's sinking in a little more. So for the loop case, do you need to know the Feynman diagram?
No.
Is there any distinction between the tadpole loop or the non-tadpole loop's momentum?
No, that is still not completely clear in the sense that these volumes give us contribution. So these volumes give us integrands, and these integrands have contribution also of tadpoles.
Yeah.
So
but you don't need to. You don't need to distinguish between them. And what about? I mean, is there any progress beyond one loop?
There is some unpublished progress by Arkan Hamad et al. In a scalar field theory. Because in the n equal to 4 super Yang-Mills, of course, there is progress because this amplitude-hedron actually captures. It's a all loop polytope for the super Yang-Mills. It doesn't go quite like this, quite like in the scalar field case where we have different polytope and different loop. There is some universal polytope that they have there. But here, yes, there is some unpublished work by Nima that I don't know when it will come out, which has gone beyond one loop, actually gone to arbitrary loops. So there are these polytopes that there is a qualitative difference between going from tree level to one loop and one loop to two loop, but it appears from their talks that going beyond two loop and beyond, there is no qualitative difference. You have the same. Yeah.
And in none of the cases you need to know. You need to refer to the Feynman diagrams.
No. Yeah, that is the kind of the goal was really to start with the bare bone kinematic space. Yeah. Yes.
Okay. Thank you.
Okay, thanks. There are no more questions that I can see, plus we are out of time. So thank you very much, Alok.
Thank you.
Thanks for a very nice talk. Please, you unshare your screen. So the next speaker is Arpan Bhattacharyya, and he'll be talking about circuit complexity and some of its applications. So Arpan, please share your screen and start. Okay, we don't hear you as yet. Arpan, can you say something?
No.
Okay.
I'm just.
Oh, that's because you're speaking. Okay, so please start.
Okay, 1 second. 1 second. Okay. So, okay, I'm starting actually. So first of all, thanks to the organizer for giving me the opportunity to present this talk in this symposium. So I will talk about circuit complexity and motivated by some conjectures coming from ADS-FT correspondence. we will discuss the circuit complexity and some of its applications in some quantum mechanical system and see what interesting things we can learn from it. And this is primarily based on these 3 works that is listed here and with this set of people. And I understand that this will perhaps be quite different from rest of the talks in the symposium, but let me see how much you can convince you about the usefulness of these things. So this is the main outline of the talk. So I will start some basic introductions and the motivation behind, at least for me, to look into circuit complexity. And then I will discuss some basic setup of this via some simple example. And then the last part will be focused on the applications and where we will try to establish that whether we can use circuit complexity as a symptom of quantum chaos and apply it to some interesting model like cosmological scenario, etc. And then I will try to summarize. So this is the, let's start with some basic introductions. I'm assuming that most of the audience are familiar with this ADS-CFT. And those who are not, just one line, ADS-CFT is something, duality between a certain strongly coupled field theory living at the boundary of this ADS anti-de Sitter spacetimes and with a weakly coupled gravity inside the bulk. And probably it is one of the best platforms to study some aspect of quantum gravity. That's it. So we'll not need much of ADS-CFT throughout this talk. So in recent times, what is happening is that various tools of quantum information theory has played an important role to understand or advance our understanding about the mechanism of ADS-CFT. And because it's a conjecture and we still don't know the proper inner working, and we can deploy a plethora of quantum information to actually to understand, sort of gain intuition about what is going on. So one example is this entanglement entropy, and there is the famous Ryuta-Kainagi prescription, which says that to compute entanglement of a boundary subsystem, one needs to compute a area of a minimal surface inside the bulk ADS. And this is a very nice geometric picture of computing entanglement entropy. And it actually, over the years, there are a lot of work has been done to establish that fact that it really gives us important lessons about how this geometry emerging from certain microscopic degrees of freedom of boundary CFTs. And this duality become more stimulating in the context of black holes. So in the figure, it is showing some eternal black hole, and we take 2 subsystems, A and A prime, sitting at the 2 boundary of the eternal black hole. And at t equal to 0, there is the blue line is the Ryuta-Kainagi surface that is connecting these 2 subsystems if you try to compute the entanglement entropy between them. Now you do a time evolution of this A and A prime. What is happening is that quickly on the right-hand side figure, you can see that quickly this extremal surface become disjoint. So basically it comes out of the horizon. So this 45-degree dashed line at the horizon in this Kruskal diagram. So this Ryuta-Kainagi surface cannot penetrate the region behind the horizon. And the time scale that is the thing, the time scale within which this happens is typically called the thermalization scale. And in the green thing, you can see the top-down picture. So it's veneered out of the throat, and it just encircling the 2 mutually, these 2 A and A prime, the subsystem. And so this Ryuta-Kainagi surface is not enough to probe certain region of the spacetime. For example, the region behind the horizon, where we think the interesting physics lies. To have then there are several conjectures have been made, and there are several new geometric quantities that have been proposed, which can actually probe the region behind the horizon. Frankly speaking, there can be many more. So we focus for simplicity on these 2 things. One is the volume generalization of Ryuta-Kainagi surface. Instead of codimension 2 surface, you take a codimension 1 volume connecting the 2 subregions. And that is known as something called a complexity of the volume. So you compute this volume as shown here and in this red, and you just maximize this volume slice that is going through the bulk and connecting these 2 subsystems. And another one is this, consider this particular patch known as this Wheeler-DeWitt patch. This is basically a domain of dependence, future domain of dependence for this bulk time t equal to 0 slice. And you define a proper gravitational action inside this patch, and you call this is like a action equal to complexity conjecture. And both of them, you can see, can actually probe the space-time behind horizon for quite a long time. So they keeps on growing, but they indeed saturate at some point, but that saturation happens later than this thermalization scales. So it can probe a considerable amount of space-time region inside the horizon. And given these properties that it keeps on growing with time, and the growth rate saturate to, for some cases, to some related the energy of the black holes, etc., they are conjectured to be dual to the so-called the complexity of the dual field theory state. Now, this motivator has to actually compute or at least define what is meant by complexity in the dual field theory side. And that has initiated a lot of study in recent times, although the technology is far from developed to actually make a comparison with holography, but at least we can compute this complexity in some simple setting and make a qualitative argument. And in this talk, we try to see how to set up the notion of complexity in dual field theory or even quantum mechanical systems, and what we can learn from it. That will be the main focus of this talk. So after this, we will not refer to any ADS safety per se. Okay. So before going to the setup, let me say something about computational complexity. So it's like a huge subject, originate from quantum information as applied to various branches like computer science, etc. And it has actually have given a lot of important insight in quantum many-body physics. So for interested audience, one can look at these references by Vidal and Ignacio Chirok, etc. But we will focus on a certain aspect of this thing known as circuit complexity. And the question we will ask is that how difficult to prepare a particular state. So suppose we wanted to simulate a complicated quantum many-body state in the lab, but typically we'll have access to a simple state, which we'll call reference state. And this state will have a zero entanglement. For example, you can create easily a state for, say, where all spins are up, like the state we can easily create. But the point is that given that state, given that accessible simple reference state, we want to build a circuit, quantum circuit, which will act on this reference state, and as an output, it will generate our target state, which is the state that we want to prepare, some quantum many-body state. And typically we'll have some bunch of gates, and we want to prepare this big quantum circuit, this thing by connecting bunch of gates. And then the question is, what is the optimal circuit? That is, what is the circuit made up of minimum number of these such kind of gates or operation, and so that we will get our target state within some specific tolerance, given some tolerance. And of course, this will depend on choice of reference state. Although in the application part that I will going to say will not so much depend on the reference state, but typically for all practical purposes, things should depend on reference state and some other things that I will mention as I go on. Okay. So given this setup, let's try to take a concrete example and see how this works out. So let's take a very simple example. Let's take this two-coupled oscillator. You can discretize the scalar field theory and get a bunch of coupled oscillator, and this is a two-coupled oscillator. We can solve the ground state for this by going to normal mode coordinate, and this is given here. So we will, and so this is the state, the ground state of the system that we want to simulate. So this will be our target state. And you can see this is a Gaussian state, so things can becomes very easy. All the calculations become very easy. And this has been like taken for Jefferson Mars, but we with Anindo and student, we actually extended it perturbatively for some kind of a non-Gaussian state in somewhat. But we will not go into that in this, at least in this talk. So now let's compute the circuit complexity, which will refer to sometimes of circuit depth, because you see we are actually counting the minimum number of gates. It's like the depth of the circuit for this target state, particular target state. So as I said that for doing this, we need to start with some reference state, and typical reference state there is a zero entanglement. So if you look at this target state, if I go back, so it's an entangled state because there is a cross term in x1, x2, x2 in the state. So now the reference state will take a simple Gaussian reference state unentangled. So it's just a x1 square, x2 square. There is no x1, x2 cross terms. And we want to build a circuit, optimal circuit. So given this given this particular problem, we can choose this following set of gate, because we say that a set of gate has to be given. And then we have to build the circuit on that given set of gate. So we choose this natural set of gate as is saying the first two is simply scale the coefficient of x1, x2, And next two will actually generate a cross term between x1 and x2, which will be needed to generate this x1, x2 term in the target state. Now, given this fourth set of gate, they will say that form a closed algebra. So these O's are form a closed algebra. And then the target will be to construct a circuit U, which will act on based build, which have been built using this gate, act on the reference state, and that will reproduce the target state up to some given tolerance epsilon. And at this, for this simple example, we can tune the epsilon to 0 to get a very precise match. But for all practical purpose, there will be error, of course, as you can see. So this is the setup. And then how to calculate that this optimal unitary. So the approach we'll take is based on this Nielsen geometric method. And I like to be devil's advocate here. Means we don't know whether this is the best way to compute or quantify complexity, but nonetheless, this is a very illuminating geometrical procedure to compute complexity. It may be difficult also to compute complexity for practical systems. So what is this? Instead of working in this discrete picture that we have discrete gate, we at first parameterize the circuit by a continuous parameter S, which runs from some 0 to capital S. And here O's are these gates, and then Yi counts some called the control function, which actually counts the number of how many times you have applied this how many times you apply a particular gate. And there is a path ordering because this operator don't commute itself. So basically this is a path order big unitary. And then you can go to discrete picture by actually just discretizing in the direction of X, and you can see delta S is basically the epsilon. Epsilon will be the epsilon. And we have the boundary condition that initially we have a reference state. So U at S equal to 0 is the initial point, it's just identity. It has to be there. And at the final, at the end point that S equal to 1, so U acting on the reference state should give the target state. Remember, this S is nothing to do with time or anything. This is just a fictitious continuous parameter in the space of circuit. So it will measure basically the circuit depth. And we can set up this fixed point, the end point of S to anything. So we choose it for S equal to 1, parameterize the S such that the circuit ends at S equal to 1, but you can reparameterize it and make it S equal to 100 or something else. But that does not essentially make any difference. So it will be just a overall factor. But remember, this is like a circuit parameterized by this S, the fictitious parameter. Now we need to find the optimal circuit, which means we need to find this optimal Yi's as a function of S. And how to achieve that? And then we take the intuition from this classical mechanics, or which says that we define a cost function, which is like you can think of it like a Lagrangian of f, some f with a function of u and u dot. Basically u and the velocity u dot, and it will be a function of y's and the derivative. And then complexity, a functional will be given by take this function, integrate over s from 0 to 1 endpoint, and then minimize this function, and the minimum value will give us the complexity. Of course, one has to do much work to relate this number to actually the counting of gates, which we have done with Anindo and Pratik. It's actually non-trivial matter, but given the time constant, I will not go into that. But we will take the definition of complexity as this one. So is the after you you have defined some cost function, extremize it or minimize it and evaluate it on that, and that minimum value is given will give us the complexity. So, and how to write down the cost function? So there are some desirable properties that we usually impose and which is listed here. And you can see if they are satisfied, these functions will behave like a distance functions on a given manifold. So there are several choices actually satisfying this, and I have listed here. So in this talk, we'll actually mainly focus on this F2, which is like a distance function, square root of yi square, this thing. And you can use the other cost functional, and for the application point of view, it will actually will not matter much. Actually, you can use any of them, but we'll focus on this for simplicity. And then what will happen? And if you note that there is this factor P of I here inside F2, and which sometimes called as a penalty factor. And geometrically, it means that some of the direction in the space of circuit has been preferred over other direction. Which means that suppose you have a set of gate, but among the set of gates, some of the gate is not easily accessible. I mean, it's very hard to build in the lab. So you actually increase the cost corresponding to that particular gate. And that is reflected by putting some cost functional. And in the geometric meaning, as I said, it actually gives it gives a weight to some particular direction in the space of gate. Now, what we do, so given this choice of cost functional, what we should do, we have to minimize this cost function. Remember that these can be written in terms of this, in terms of delta S u times u inverse. And then we can define a metric given this y. From this ys, we can define a metric that capital Gij will involve this information about the penalty factor. And for this talk, we will set it to actually 1. But you can bring it, and essentially actually also that will not make much difference of what I'm going to show in the later part of the talk. So, and you then find a geodesic on this metric and evaluate the action on this geodesic. You can show that this cost functional will be minimized on this geodesic, which we find on find for this metric. And to just elucidate this process, so what we should do from the practical point of view. So for our case, the wave function, the psi of s, for both the reference and target state can be written into this particular form. So where v's are some basis, where the two oscillator x1 and x0, and then this matrix will take some form, which we have solved. For s equal to 0, it's a reference state, s equal to 1 is the target state. And you can see that this is a particular convenient way of writing the wave function, as we will see. Now, given this basis, we have this, remember, we have this gate that will act on this wave function. So given this basis, these operators, these 4 operators act on this basis, and we can find the matrix representation of these operators. And we will see that with this choice of this operator, there's nothing but a GL2R generators, basically. And then we write the capital YI in terms of this metric representation of this O, and what boils down to actually finding a geodesic on a group of GL2R manifold. Also, we parameterize our unitary, which is a GL2R unitary, as R times SL2R. If the parameterize is given, we choose the penalty factor in this, as I said. And then the line element becomes this. Now we have to solve the geodesic on this background, and the boundary condition boils down to this condition, that at is this u in terms of A, we have this boundary condition, and explicitly in terms of this coordinate, we have these 2 set of boundary conditions. And given this boundary condition, we found the geodesic on this background, and that can be done very easily for this explicit example, but maybe more complicated for all other many body systems. And given this geodesic, then the thing is that we can show that this functional, the complexity functional, gets minimized on this geodesic. In fact, for this 2 oscillator case, one can explicitly check that the geodesic is actually minimal, not just extrema. And for example, if you took this kind of cost functional, you just evaluate this cost functional on this geodesic and integrate it from ds from 0 to 1. And finally, you can write the complexity in terms of normal mode coordinate, which takes the particular form. So in short, what we do is that we first parameterize the circuit by some continuous function, and given the choice of gate that decide the underlying group manifold, and we do a geodesic, we find the geodesics given a certain boundary condition on the group manifold, and then evaluate the complexity functional on the geodesic. And it gets minimized, and the minimum value corresponds to our so-called circuit complexity, and which indirectly related to the minimal number of gate from which the circuit is built. So this is the strategy that we'll follow in the coming section, where we actually try to apply this procedure to some interesting quantum mechanical system and see what physics we can learn from it. Okay. So I will now discuss the application part. So the main goal is to use this complexity and try to establish whether we can actually use it as a symptom of quantum chaos. So before we jump to the main calculation, let me say something about the quantum chaos. We know that classical chaotic systems are characterized by hypersensitivity to perturbation in the initial condition under the Hamiltonian evolution. So we know that the initial trajectories that diverges in the phase space, and it is highly sensitive to the initial condition. This is how the notion of classical chaos comes into play. But for quantum systems, we cannot actually momentum. Of course, there is this uncertainty principle. And also we know that volume occupied by a single quantum state in the classical phase space is basically h bar by 2 pi whole to the power n. N is the number of degrees of freedom, the underlying system. So for large system, which is typically all these quantum many-body systems are, we don't have the luxury to follow individual orbit and see how they are diverging. So new diagnostics are needed. So at this point, I like to emphasize that one should not think about quantum chaos is like taking a classical chaotic system and quantize it. There are many counterexamples to it, and we don't even know a proper definition of quantum chaos actually. So quantum chaos, when we say quantum chaos, it has been, we keep in mind that there are certain observables or certain quantities we can compute for the underlying system and then behave in a particular way. So it is rather right to say as symptoms of quantum chaos instead of saying the diagnostics of quantum chaos. So this one should keep in mind. It's not just taking a classical chaotic system and quantize it. And for a very good review of this, one can refer to this paper and this PhD thesis actually. So there are many such symptoms that has been developed over the years, starting from Wigner in 1950, which actually deals with the statistical properties of the energy spectra. So what he proposes is that you can compute the distribution of eigenvalue spacing of nearest eigenvalues in a quantum chaotic Hamiltonian, and this distribution is similar to the one is the Gaussian random matrix ensemble, and this is the famous Wigner distributions, which actually developed dealing with the spectrum in the various nuclei. But the computation of the eigenspectrum is quite taxing actually. So other symptoms are desired actually. And one such popular one which has been used in recent times is so-called the out of time order correlator. You take two generic operator A and B and you compute this out of time order correlator. And you can take the thermal expectation value if you want actually. So beta is the inverse of the temperature. And if you look at this, so if you look at the arrangement of the operator A and B, you can see why the name is out of time order correlator. Of course, only restriction is that you should not take A and B as some kind of conserved current or conserved trace energy tensor of the theory. And this can be also related to this OTOC can be related to the out of time commutator square of outer time order correlator, and which is given by this relation. And you can view this is nothing but a quantum analog of the classical expectation value of this deviation of the trajectory of the space, which actually gives you the Lyapunov exponent. So from the deviation of the trajectory, you can compute so it deviates exponentially, and that from that you can actually infer this coefficient, which we have known as the Lyapunov exponent, which is actually gives you the quantitative measure of these chaotic systems. And there can be more than one Lyapunov coefficient in principle, in general, actually. So early time characteristics decay of OTOC is found to be like this. So OTOC decay in the early time is like, if you normalize it properly, it's like 1 plus some number time exponential of this some lambda of L times T minus T star. And this lambda L is something called a quantum Lyapunov exponent. And it can be shown that most of the cases this lambda L matches with the largest Lyapunov exponent coming from the corresponding classical picture, if at all there is a classical picture, hence the name actually, by comparing with the corresponding classical model. And T star is something called a scrambling time. Where it measures the time after which this decay sets in. So this is also these two parameters, lambda L, quantum Lyapunov exponent, and the T star are the two characteristics quantities that one like to compute to have a measure of the underlying quantum chaotic system. And recently it has been well explored in holography, and some chaos bound is conjecture by Mardashana Schenker Stanford, which is say the Lyapunov exponent is bounded by 2 pi by beta. Beta is the inverse temperature of the black hole. But it has its own drawback, this OTOC. So its reliability actually breaks down at late time because it's become highly theory dependent. And even for some well-known single particle quantum chaotic system like this stadium billiard ball model and some quantum spin chain, where we know they are like chaotic by comparing with their corresponding classical part, we can compute OTOC for them, but we don't see these characteristics exponential decay. And so we need another measures or another symptoms to characterize this quantum chaos actually. So in this context, there is a pertinent question to ask that whether we can use complexity as diagnostics of quantum chaos, and that will give sort of an information theoretic angle or information theoretic diagnostics of this quantum chaos. So that's what I will like to show, that how we can use this complexity to infer about these two particular characteristic things, this lambda L and T star from underlying quantum chaotic systems. So before I going to say, there is an illuminating diagram that I borrowed from this paper. There is a zoo of measures or symptoms of quantum chaos. You can see there are a plethora of things that we use. You can see OTOC, Roche Deco, spectral form factor, many things, and there are some relations among them has been established actually. But for this talk, we will consider the complexity. This is our hero of this talk for the moment. And of course, in certain cases, you can actually relate this complexity to other diagnostics that we have done in one of our paper, but I will not go into that. But this is, remember, this is the sort of summarize the status of what is the symptoms of quantum chaos currently explored in the energy theory literature. Okay. So now let's consider the basic model. So we'll use something, a very basic model, inverted harmonic oscillator model. And as we know that whenever we try to establish a new thing in physics, we resort to harmonic oscillator. It gives us a robust laboratory to test in, various interesting physics. And per se, it's not a truly quantum chaotic model because in a stricter sense, it's basically, we have the classical unstable fixed point at x equal to 0, p equal to 0 of this inverted harmonic oscillator. It's not a true quantum chaotic model in a strict sense. It's a toy model, but nonetheless a very powerful and interesting toy model. And it has been shown that in the wider context in the field of quantum chaos, this model can be actually used to infer a lot of interesting physics. So this is some references here is mentioned for the interested audiences. Even it can be some sort of an experimentally realized. Also, it can appear as a local maxima inside various interesting potential. For example, you take this Mexican head potential, and if particles start at this maxima point, it will show an inverted regime for a certain time. So it often happens that for a short time interval, a chaotic system may be approximated by an inverted harmonic oscillator model. So that's why it plays very important role. Although, as I should emphasize that it's not a true quantum chaotic, but the thing that I'm going to say, I will give you a proof of principle argument that how complexity can be useful to as a symptom of this quantum chaos.
Arpan, you have 5 minutes.
Oh yes. So the setup is that we have this Hamiltonian, where this omega is m squared by lambda. So we have a tunable parameter lambda. So when m square lambda is a free particle, m square greater than lambda is harmonic oscillator, m square less than lambda is the inverted harmonic oscillator because the sign changes for m square lambda. And the reference state we take is the ground state of the harmonic oscillator, which is given here. And the target state is being constructed by taking this ground state, then do a time evolution by h, and then do a backward time evolution by h plus some perturbation, delta h. I mean, here the perturbation boils down to perturbation in the lambda. Then given this targeted reference state, we can compute the complexity that what we have described earlier. And then we can show that if the oscillator is regular, then the complexity just oscillates basically for this system. But if it is inverted, then it's a remarkably different behavior. So it actually becomes very small up to certain time and then shoots up and increase actually linearly. So then we see that there are two characteristics scale here. One is this time when this linear growth happen, and the slope of this linear regime. And we plot both this time ts and this slope with respect to this coupling lambda, and we get this plot. Furthermore, we can compute the out of time order correlator for this inverted harmonic oscillator, and we can find from that the Lyapunov exponent and this T star scrambling time. And this is just a oscillator model, so I should not say scrambling time, but it's the RN phase time basically. So lambda is basically this mod of omega lambda L, and T, this T star of the scrambling or the RN phase time, is basically related to 1 over lambda log of 2 pi h. This is like a very well established result. So if we compare this, and also we take these two things and plot with respect to this coupling lambda, and if you compare this plot with our previous case, they are precisely the same. So from here, we can actually establish the slope of the complexity is actually related to the Lyapunov coefficient, and this pickup time is related to the scrambling time of the RN phase time. So we can see that we can actually find out the characteristics properties of the this chaotic system from analyzing the complexity. And one more check is that, so we have seen that we have done backward evolution with the H plus delta H, slightly different H, but how slight is that? So we can plot this complexity for various delta, small changes, but we see that although the pickup time changes, but the slope remains same. So the information of the Lyapunov coefficient is robust from the complexity. We can generalize towards the more field theory type of model. You take a two coupled scalar field with the irrelevant deformation, and if you discretize on the lattice, you get a inverted mode and the non-inverted mode. And if you can focus on this, you can do the similar analysis and found the Lyapunov exponent information from the complexity, from the slope, by analyzing the slope of the complexity, which matches with the corresponding result from the out of time order correlator. But last but not the least, actually, this is the last thing that I will end. We apply this concept for the scalar cosmological perturbation, actually. And we will consider a flat FRW metric, which is given here, and eta is the conformal time. We consider background scalar perturbation, which is say that we consider there are two sources which coming from the scalar field itself. Another sources is the coming from the metric, scalar part of the metric fluctuation. And then we have the Einstein action, and we consider only minimally coupled scalar field theory, and up to the quadratic coordinate fluctuation of the scalar field, the action can be written in there. So capital curly R is the curvature perturbation, and we can do a variable change using this Mukhanov variable, and the action becomes this, and then do a Fourier transformation and write this V of k in terms of creation annihilation operator, and then the Hamiltonian, resulting Hamiltonian becomes this. So you can see there is a free part and there is a inverted harmonic oscillator part, and late time the inverted harmonic oscillator part dominate. So the scalar perturbation part and the model up to the quadratic coordinate fluctuation becomes our inverted harmonic oscillator for this scenario. And you can do it for the tensor perturbation also. And to end, let me show the results. So the reference state is the 1, 0 for the usual oscillator, and the target state is by time evolving the reference state by this Hamiltonian I just showed. Of course, to compute complexity, we need to know the background, the A, the scale factor, and we can analyze it for many different backgrounds. Here I just listed some, like the de Sitter one, the exponentially growing one, and then the radiation and the matter dominated one. De Sitter where the universe is expanding, but you can generalize it to for other accelerating, non-accelerating, many other background. So if you consider de Sitter part, and you can show that if you compute complexity, and this also have the same characteristic behavior, that it remains small and then shoots up and increase linearly, and you calculate the slope, and we find that the slope is actually bounded by the Hubble constant. And in this case, that you can make with the chaos bound. So basically dc dt is proportional to the Lyapunov coefficient, which is less than 2 pi t. T is the temperature defined for the cosmological horizon, which is actually related to the Hubble constant. And this is very similar to the chaos bound, and we shown that we can find the Lyapunov exponent corresponding to the cosmological evolution of the perturbations of the universe in the de Sitter regime. And it's just a conjecture. Subsequently, by direct computation of out of time order correlator, both in the gravity side and in this model, it has been established. Indeed, the Lyapunov coefficient is related to this h by root 2. So this gives the consistency check. So I will end here by summarizing that we give a proof of principle argument of circuit complexity as a symptom of quantum chaos. For that we inverted a harmonic oscillator model. we can explicitly extract the information about the Lyapunov exponent and scrambling time from the complexity. And we have applied it to several interesting model like cosmological model. And also this is just a toy model, so we need to extend it heuristically model, which we are working in like a rotor, kicked rotor and kick top model. And certainly it will be interesting to expand this for a non-trivial chaotic field theory. And one thing that we are finishing is to apply it for the open system. So many of the chaotic behavior rise, in fact, if you couple the system with the thermal butt and then trace out the system. So you can analyze the subsystem, analyze the reduced density matrix and try to compute complexity for that. And that gives also a interesting feature. So lastly, I will end with the thing that these are only baby steps to understand complexity in quantum mechanical system or quantum many-body system. There are a lot to be done. At least the take-home message is that even if we cannot immediately connect with the holographic conjecture, but there are novel features one can uncover of the underlying field theory using the circuit complexity, and hope to be like to push this thing and see what interesting things we can learn. So I will end.
Thank you very much. So thank you, Arpan. Now, if there are any questions, please raise your hands. Those who have questions, there are none in the chat right now. I'm also, Debashish has a question. Please go ahead.
Hi, Arpan. Nice talk. Thank you. The last part where you talked about the cosmology, of course, you had to rush through it. What do we learn about cosmology from this approach, and can we check this from the data that one gets from Planck? Like, can you relate
data
it to
part?
NS?
I don't know, but what we learned actually. So here, I just show you some background. So we have did a thorough analysis of this different background actually, not just de Sitter, but not just the accelerating universe, but the but for the other contracting, decelerating, whatever the other
No,
models.
I understand.
Also, actually.
Yeah, I understand
So,
about the theoretical
thing is
part.
that you can show the de Sitter regime. De Sitter ones are the ones actually that satisfies the chaos bound from the complex. So the complexity.
No, I understand. I got the point about the theoretical part, but I'm asking, suppose can we match it with the?
I wanted to say that from the point of view, suppose you wanted to analyze this theory, from the complexity point of view, I will say that de Sitter theory are more complexity wise, it is more favorable. So you can simulate this field theory like a bigger picture in quantum computer easily compared to the other cosmological model. And data part, I don't know at this point.
No, but can you relate it to the parameters like NS or something, the spectral parameter, which are
spectral parameters. So spectral parameters. So this information of this low roll, etc., is there in this complexity, and one thing that I can relate this time scale actually also relate to the number of e-folds, basically this time scale where this thing shoots up. This time scale actually related to the number of e-folds, and this is precisely the time scale, at least what I am aware of, that also appears in this trans-Planckian cosmic sensor chip conjecture actually. So some existing time scale does appear inside this complexity.
Okay. So it can be related to how much e-fold one had during the inflation and this kind of
yes. So I didn't tell you the I didn't tell you the physical picture actually. So why we get the exponential growth? So initially, when the mode is inside the horizon, complexity don't grow much, because the squeezing part, that the inverted harmonic oscillator part, does not play that much role. So when the mode exits the horizon, the squeezing grows, hence the complexity grows. So this is the time, this time scale is basically saying that this is the time takes the mode to exit the cosmological horizon. And if you do a full thing, like this is the de Sitter part, and then there is the, say, radiation part, actually complexity decreases because the mode re-enters the horizon, and then becomes saturated. So this is the full physical picture, which I didn't show actually here.
Thank you.
Okay, thank you. So we are out of time now. So thank you again, Arpan, and thanks to all the speakers of this session, Gautam, Alok, and Arpan, for their very nice talks and for essentially keeping in time. We started 5 minutes late. We're ending 7 minutes late. So thank you all for attending. So session is over.
Thank you, Sunil, and thanks to all the speakers. Thank you.